This is question 3 from Step 3 2010, and you can also find it as question 1 from the Step 3 Complex Number Support Programme. So in this question we're going to delve quite deep into complex numbers, and in particular roots of unity. We're going to look at this thing which is the primitive roots of unity, and this polynomial you get, Cn of x, which if you're interested or want to read more about it, they're called cyclotomic polynomials. Okay, but we don't need that. Let's get started with this definition, because this is a new definition. Any integer n, the complex number a is a primitive nth root of unity if, okay, a to the n equals 1, that's the bit which means it's a nth root of unity, so you're probably familiar with that already. And the primitive part is this, so there's no value of m, which is between 0 and n, so basically just less than n, where a to the m equals 1. So this basically means a needs to be an nth root of unity, and if we're counting up from 1, a needs to not have been a root of unity yet before. There's no integer less than n where a is already been a root of unity. Okay, so to try and get some kind of understanding what this is, let's have a look at this table. Okay, what I'm going to do is I'm going to work out what the roots of unity are first. I will then in this column work out what the primitive roots of unity are, but let's start just with the roots of unity. So all I need to be true is that a to the n equals 1. Starting with n equals 1, that's quite straightforward. There's just going to be 1, which is 1. That's why it's unity. Unity means 1. Okay, for n equals 2, I need to solve a squared equals 1. Nice and easy. That's plus or minus 1. For n equals 3, it starts to get a bit more challenging. So we know that we need to solve a cubed equals 1. We know that 1 is going to be a solution, so we could factorize that out and get a quadratic, which we could solve. But to generalize this, it's going to be helpful to remember something you do in complex numbers, which is to write 1 like this. So you write 1 as e to the 2 pi I k, where k is just any integer. Once you've got that, you can now take the cube root of both sides, and a is e to the 2 pi I k over 3. We know we're looking for 3 solutions because it's a cubed equals 1. So we just change our values of k from 0, 1 and 2 to get our 3 third roots of unity, and there they are. So for k equals 1, that'll be e to the 2 pi I over 3. For k equals 2, that'll be e to the 4 pi I over 3. And this 1 there is if you take k equals 0, or in fact 3. Okay, so that's that. Let's carry on, fill in the rest of the table. So a to the 4 equals 1, pull the same trick. We'll get those as our 4 fourth roots of unity. A equals 5, again, same trick. These are our 5 fifth roots of unity. And for n equals 6, here are our 6 sixth roots of unity. So nice and straightforward, and we know how we have them all because there should be, for example, 6 solutions here, and there are. Okay, before we go on to the primitive roots, let's just see if we can simplify these at all. So 1, 1, negative 1 there, all really straightforward. E to the 2 pi I over 3, so this is the complex number with radius 1 and argument 2 pi over 3. That's not anything obvious, but if we continue down into the n equals 4 case, let's have a look what these are. So 1 is here, I have radius 1, so this circle represents radius 1. E to the 2 pi I over 4, so that has argument 2 pi over 4, pi on 2. That's going to be up there. E to the 4 pi I over 4, that's going to be e to the pi I, isn't it? Which we know is negative 1. And e to the 6 pi I over 4, it's going to have argument 3 pi over 2, so down there. So there are, so a nicer way to write these are actually 1i, negative 1, and negative I. If we look down at n equals 5, there's not really any nice way we can simplify them. But down at n equals 6, we can start sort of cancelling some of these arguments down. So again, what does this mean? There's 1 argument of 2 pi over 6 or pi over 3 is there. 4 pi over 6 or 2 pi over 3 is there. Argument of 6 pi over 6 or pi is there. Well, we know that one's going to be negative 1. E to the 8 pi over 6i, the argument cancels down to 4 pi over 3. And e to the 10 pi over 6, we can rewrite that as argument 5 pi over 3. But basically all I'm doing is I'm cancelling down these arguments here. And I know that I can cancel these fractions, so I can rewrite these 6 roots of unity like this. Okay, nothing drastic, but I do see here that I've got -1. And I know I've already had -1 already, in 2 places in fact. Okay, so I'm just going to update that table. That's the roots of unity. That should be A-level knowledge there, or further maths A-level knowledge for sure. Let's try and look at this definition of primitive roots of unity. So all it means is it's a root of unity, so it has to come from this column, but it's not been a root of unity already. Okay, so for n equals 1, there's 1. N equals 2, what are the primitive roots of unity? Well, we've already had 1, so don't include 1. So the primitive roots of unity is -1. Note here, n equals 2 does not mean I need 2 primitive and second roots of unity. In fact, the number of them is something that we're kind of going to have a look at in the rest of the question. Here there's only 1. Alright, next one. I've already had 1. I've not had these complex numbers yet. I know they're not 1 or -1 because they have sort of an imaginary part. So these 2 are going to be primitive third roots of unity. N equals 4, I've had 1 already. I've had -1 already, but I've not had I and -I, so in there you go. N equals 5, I've had 1 already. Now, you might need to convince yourself a little bit that we've not had these already, but if you think about the power here being the argument of the complex number, then it's clear we've not had anything with argument 2 pi over 5 yet, or 4 pi over 5, or 6 pi over 5, or 8 pi over 5. So they're all primitive fifth roots of unity. And finally, for n equals 6, I've already had 1. We haven't had e to the pi over 3, but we have had e to the 2 pi over 3. Okay, and the step of cancelling the fractions means that we can notice that quite easily. So I can cancel that one. I've had -1 already. Have I had e to the 4 pi over 3? I have, so not that one. I've not had e to the 5 pi over 3. So those 2 are my primitive sixth roots of unity. Okay, I should mention at this point, we're kind of ignoring the question, but the first part of the question does ask you to write down the 2 primitive fourth roots of unity, and so they're here, I and -I. So that's the first kind of STEM part of the question done. But I definitely would draw a table like this if I was doing this question, just so I get more of a feel of what's going on here. Okay, the next bit of the question in the STEM asks us about this polynomial Cn of x. So the definition here, it's a monic polynomial. That's just another way of saying the coefficient of the highest power is 1. The roots of Cnx equals 0 are these primitive roots of unity with no repeated roots. So I have gone through the effort of working out what these primitive roots of unity are, so we can go ahead and work out what the polynomial is. The stem of the question does actually ask me to work out what C4 of x is equal to, so we will get there, and it will go into this grid here. Okay, but let's start with n equals 1. I need a polynomial in x whose only root is 1. What's that going to be? Well, it's just going to be x minus 1. Doesn't have any repeated roots either, so x minus 1. It's monic, so it can't be like 2x minus 2. X minus 1 is the only thing it can be. Okay, next one. The only root needs to be -1. So what's it going to be? It's going to be x plus 1. It's the only thing it can be. And that is our second polynomial C2 of x. Okay, it gets a bit harder here. Okay, there's a few ways we can go about it, and actually I think the solutions for the step support program do it differently to what I'm going to do. I think they take x minus e to the 2 pi over 3 and multiply it by x minus e to the 4 pi over 3, and you can expand that out and work it out. What I'm going to do is I'm going to say, well, I know these are all roots of x cubed minus 1, because that is the same as it being a root of unity. But I've taken out one root here, x minus 1. So if I factorise out x minus 1, do it in whatever way you want. If you want to divide it or just inspection is nice and easy, and this is what I'm going to get. I know that x minus 1 needs to not be a root. So I ignore that. So my polynomial C3 of x can be what's left, x squared plus x plus 1. And here there's 2 third primitive roots of unity, and so it makes sense for there to be a power of 2 here, an x squared, a quadratic. Okay, next one, and this is what the question asks for, what is C4 of x? I'm expecting a quadratic because I've got 2 primitive fourth roots of unity. And here there's a load of ways to go about it. Okay, you could do x minus I multiplied by x plus I. I'm just going to stick with my same method. I know that all the roots of unity are the solutions to x to the 4 minus 1. I'm going to factorize out this polynomial. I know that 1i minus 1 and minus I are roots, so it's going to go like that. But I'm going to cancel my 1 and negative 1 roots, leaving me with x minus I, x plus I, which I can multiply to x squared plus 1. Okay, however you show it, as long as it's clear, you get what they want in the question, which is c4 of x is x squared plus 1. Just for good measure, I'm going to continue, work out c5 and c6. In fact, that is what part 1 of the question is actually going to ask me to do. So for c5, I know that my fifth roots of unity, so of x to the 5 minus 1, the only root I'm excluding is 1. So I'm going to factorize out x minus 1, and that's what I'm left with. Because 1 is the only root I'm excluding, I therefore know c5 of x needs to be that. The only thing it can be. It's got a power 4 polynomial, there's 4 primitive roots of unity, so I know that must be right. Finally, for n equals 6, this time I'm cancelling quite a lot of roots, but I can just go through and do the factorization. This one, it probably is easier to just do x minus e to the pi over 3 multiplied by x minus e to the 5 pi over 3, and you can look at the step support program solutions for that if you want. I'm just going to continue with the same method. So I'll factorize out x minus 1, cancel that. From what's remaining, I'm going to factorize out x plus 1, because I know that negative 1 is a root. And this might be a harder one to spot, but again, you can do polynomial division or just spot this. And then finally, factorize out, and again, this might be quite hard, but this the way that came to my mind, factorize out x squared plus x plus 1. Now, why do I want to factorize that out? Well, it's because the two roots I've got left to get rid of are e to the 2 pi over 3 and e to the 4 pi over 3. And the polynomial that has those roots are up here. It's the third primitive root of unity are those two. So I need to factorize out c3 of x basically. If I do that, I'm left with x squared minus x plus 1. Okay, so it happens now that I have actually done all of the stem of the question and all of part 1 of the question. So I'm ready to go on to part 2 of the question now. This is what I was saying, the alternative is to do this, and you can read the solutions for that. Okay, part 2 of the question. Find n such that Cn of x, x to the 4 plus 1. Now, the first thing to check is that we've not had that yet, and no, we've not. None of these count, so I know that n is going to be bigger than 6. There might be some sort of quick way to think about this, but let's just try the next options. N could be 7. So these are the 7th roots of unity. What are the primitive 7th roots of unity? Well, I'm going to get rid of 1, and if I check on my table, I'm not going to get rid of any of these. Okay, so I know, therefore, that the degree of the polynomial C7 of x needs to be 6, because there are 1, 2, 3, 4, 5, 6 primitive roots of unity here. Okay, so it's not n equals 7. Let's try the next one, n equals 8. Here are my 8 roots of unity, my 8th roots of unity. Which ones can I get rid of? I can get rid of, I'm just going to cancel them down so I can compare the fractions easily. Which ones have I had already? So I've definitely had 1. I'm going to notice that actually e to the pi I over 2 is I, e to the pi I is negative 1, e to the 3 pi over 2 is negative I, so I can see that I've also had I and negative 1 and negative I. Have I had any of the other ones? I can check my table. No. This has 4 primitive roots, so it might be n equals 8. We don't know yet, but we need to check that. It's got 4 roots, and so that might have the polynomial of x to the 4 plus 1. Let's work it out. So where are these roots? There they are. There's 1i, negative 1, and negative I, which I'll keep in blue because I've crossed them out in blue. And the 4 remaining ones are there. Okay. So if I take my equation x to the 8 minus 1, This is like difference of two squares, isn't it? I can change that to x to the 4 minus 1, x to the 4 plus 1. And I'm going to notice that the roots that I'm getting rid of, 1i, negative 1 and negative I, well, they are my fourth roots of unity. And the picture might help you see that, actually. My blue ones here are just the fourth roots of unity. And the equation for the fourth roots of unity is x to the 4 minus 1. So whatever way you like to see it, I can get rid of that factor of x to the 4 minus 1 and convince yourself and the examiner that you're left with as your C8 x to the 4 plus 1. So that answers part 2. N here is 8. Okay, part 3. Given P is prime, find Cp of x. Now, when I first read this, I thought this is a bit sort of wild, really. I've just spent ages working out only 6 Cn of x's, and now you're basically asking me to find an infinite number of them, because what's P? There's an infinite number of prime numbers. So to try and get a sense of a pattern, let's look at what we've found out so far. So for n equals 2, C2 of x is x plus 1. Next prime number, n equals 3, x squared plus x plus 1. Next prime number, n equals 5. That's my C5 of x. And I've done 7 actually, but I didn't actually go through the details. So these are the 3 I know. Can you spot the pattern? Hopefully you can. If n is some prime number, then it looks like my Cp of x is going to be this thing here. Okay, and maybe a good thing to check would be n equals 7, because we worked out there were 6 roots. So you could have checked for p equals 7. This gives you x to the 6 plus x to the 5 plus all the way down to x plus 1. So that's my guess, but I have not proven this yet, even though it doesn't explicitly say in the question. Let's try and prove this, because you need to do that for full marks. So the pth roots of unity, so again, not the primitive one, just the roots of unity, are this. So I've done exactly the same trick. Okay, I've done e to the 2 pi I k over p and written k through the powers all the way up to p minus 1. So how many of them are there here? There needs to be p roots. Okay. Since p is prime, the arguments of these complex numbers are 2 pi over pk. As I say, this is for values of k from 1 through to p minus 1. Not including 1 here because I know I'm going to get rid of that. So that would be like the pth root for k equals 0. But the arguments of the remainder of them are 2 pi k over p. Now p is prime, so this fraction is in its simplest form. We can't do that simplifying step. And therefore, the denominator p, as I say, is prime. If you'd looked up your table, this argument would not appear anywhere else. Okay, you can see here, for example, that n equals 5. Nowhere before here did the denominator of the argument have a 5 in, or could it? For n equals 7, we know that the arguments are all going to be, it's going to be 2 pi over 7, 4 pi over 7, etc. Nowhere before that by the denominator 7. Okay, so I knew that they were all unique new roots of unity. Okay, so therefore these p minus 1, excluding the 1, are all primitive roots of unity. So getting rid of that x minus 1 factor, I know that Cp of x is that polynomial. Maybe a step that I've skipped here is actually doing this factorization here in this step. If you need to do long division to do that, you could divide x to p minus 1 by x minus 1, or you can just spot it and see that this is going to expand out to x to p minus 1. Okay, so that's a proof. Maybe you need to be a bit more careful about this step here when you're working it out, but we've seen here, answered part 3, this is Cp of x. Alright, on to the final part then. It says that prove there are no positive integers q, r and s such that cq is cr times cs. Alright, so for this, again, a general result, this inclusion of the word no hopefully makes you ring bells that it might be a good idea to do a proof by contradiction. Okay, because we can suppose as our first step for a contradiction that Q, R, and S are positive integers such that CQ is equal to CR times CS. Okay, so we'll set this situation up. Let's try and get an absurd result, a contradiction. Okay, let A be a primitive Qth root of unity, so CQ of A equals 0. Okay, fair enough. But then what's going to happen if I substitute A into this right-hand side as well? I know that CQ is 0, so this is just 0. On the right-hand side, I've got CR of A times CS of A. So that's what I've written here. 0 is CR of A times CS of A. Just like when you've got a quadratic factorized, this means something times something is 0. So either CR of A is 0 or CS of A is 0. Two cases. And in both cases, let's do this one first. This means that A must be a primitive rth root of unity. Okay. But to be primitive, and you can look back at the definition if you need to be, this means it can't have been a root of unity before. So the only possibility, which it is a possibility, but the only possibility is that R equals Q. If R equals Q, thinking about what our equation is, we've got CQ of X be equal to, and then CQ of X again, CS of X. So we can cancel the CQ of X, and leave us with CS of X being equal to 1, but this is impossible. And since, and again, you can look back at the examples we've done, whatever the value is, whatever the nth root is, if you take e to the 2 pi I over that, that is going to be a primitive root for any integer s. Okay, so every polynomial Cn of x has at least one root. Therefore, this is a contradiction, right? You can't have a Cn of x be equal to 1. Let's repeat the argument over here. So this is the case that Cs of A is equal to 0. So then A is a primitive S root of unity. It's primitive, so it must be the first time it's happened. Therefore, Q must be equal to S. We know that A is also a qth primitive root of unity. So similarly, CR of X is going to be 1. But if you took e to the 2 pi I over R, then that would be a primitive root for R, and so that is also a contradiction. I've got my lightning bolt contradiction symbols here. Okay, so the crux of the argument here is that you cannot have a polynomial Cn of x be equal to 1. That is not possible. And therefore, because you've got this product thing, basically you're saying if the left-hand side is equal to 0, and then one of the right-hand sides is equal to 0, and you cannot have this possibility of one of these polynomials just being 1. So that's the contradiction. So there cannot be any positive integers Q, R, and S that satisfy this. And that's the question done, really. So quite a nice question if you like exploring these complex numbers, if you're comfortable with the idea of nth roots of unity, and you were able to understand what this extension meant for it to be a primitive nth root of unity. This proof, make sure you do understand what's going on here, and they've written it up quite nicely in the solutions as well if you want to read an alternative explanation.